Hi, thank you for joining me. My name is Augustin Vanrietvelde, and today I will present to you my work with Giulio Chiribella on the coherent control of quantum channels. So this work comes from a draft that will soon become a paper of the same name. This story, to give a very brief summary of the story, it's the following. There is a well-known no-go theorem saying that universal coherent control, and we will go in detail about what this means, universal coherent control cannot be done. It is not possible. So we'll see that this corresponds to the fact that you cannot have a supermap that turns a given gate into its associated controlled gate. Now, what we prove here is that, in fact, it can be achieved, universal coherent control, but to achieve it, we need to use slightly different resources than the ones that are presented here. Namely, we have to use sector preserving channels. And we are going to describe what those are. So probably to some of you, especially those who know about the reference that you can see at the bottom, some of the ideas that we present here will not be groundbreaking. This is normal. Our point here is to use ideas that have been presented in past research to apply them specifically to the task of coherent control and to explore in depth what this means for these, what they entail for this specific task. So here we will tackle the control of general quantum channels, the two control, that is the control between two possible channels, and a new notion that we call composite control. We will also use a framework that we developed recently that is called rooted quantum circuits. You don't necessarily need to know about rooted quantum circuits to follow this talk, but some of the graphical notations in particular that we use come from this framework. So you are very welcome to see the QPL talk called rooted quantum circuits if you want to know more about them. All right, so let us first define what coherently controlled channels are in the first place, which is not that straightforward. Well, for unitary gates, it is rather straightforward. If you take a unitary gate on a target system S, then its associated controlled version is the unitary gate acting also on a control qubit that will be defined by the fact that it does nothing if the qubit is in state 0, and it applies U on the target system if the control qubit is in state 1. So this shouldn't be a surprise to any of you. Now, of course, it is very important that it is a coherent control. Let's note that it is well defined only when you do it at the level of unitary linear maps. But if you look at unitary channels, then this becomes ill-defined because the unitary channel will be defined only up to its global phase, whereas the global phase will become physically meaningful in the case of the controlled unitary. And that brings me to the case of general channels. So now we take possibly noisy channels, curly C, still on the target system S. Now, what would we mean by the coherent control of it? Well, it turns out that you have several possible versions of it. To see that, you can take a cross representation of C given by the operator Ci. So let's remember that taking a cross representation, you can have lots of possible cross representations, and that is going to be important for this talk. And then you define a vector with amplitude, a vector alpha I with total amplitude 1, and you define the cross operators of the controlled operation in this way, with this amplitude alpha I being applied to the branch where the identity is applied for each of the cross operators. So this is characterization that has been described already. Now, an interesting thing that had been acknowledged also in this past reference is that this is redundant characterization, because for some choices of a cross representation and of amplitudes alpha i's will lead to the same version of a controlled channel for C. Therefore, it would be interesting to have a non-redundant characterization that has been done in the reference that you can see here. Here we present this in a slightly different way. The idea is that the choice of a controlled version of a channel is in one-to-one correspondence with just picking one cross operator of this channel and saying that it is a pinned cross operator. So the way you do it is that you take one cross operator C1 of the channel C, you complete it into a general cross representation Ci, and then you define the cross operators for the controlled channel, as you can see on the right. So as you can see, C1 will be the pinned cross operator, and it will be the one that has full coherence with the branch in which the identity is applied. So now the theorem that we prove says that any controlled channel can be put in this form. So you can change its cross representation essentially to find this cross representation. And on the other hand, this is now a non-redundant characterization. So any different choice of a pinned cross operator, even if it's, for example, the same cross operator up to the global phase, even that kind of a different choice would lead to a different controlled channel. All right, now we can maybe define the control between two different channels. So now the situation in which you say that you have two channels, A and B, and you want A to be applied if your control system is in the state 0, and B to be applied if your control system is in the state 1. And now note that here we can now take the input and output systems of the control of the channels to be controlled. We can take these systems to be of possibly different dimensions. So what would be a version of control between A and B? Now, once again, we can look at the cross representations, and then we can see that the control will, all the possible versions of the control can be given by picking a cross representation of A and a cross representation of B and doing something similar to what we have done before. These can be made non-redundant by fixing the cross representation of A to be one of minimal length and then varying over the cross representations of B. And doing that, you can have a non-redundant characterization of the possible two controls. So now let's go to the core of this talk. That is, what are the resources that you need for coherent control? And we'll see that these resources are sector preserving channels, and that the conversion between the two is done by supermap called control supermap. Let's start with the no-go theorem, which has been proven numerous times in the literature. It's just one reference, but there have been lots of different ways and different perspectives from which people have proven it. So here we will express this no-go theorem in the following way. So we consider supermaps, that is maps that act on channels and output other channels. And now there exists no supermap that acts on channel on the target system and that gives channels acting also on the control system. There exists no such supermap that maps a unitary to its associated controlled unitary. That just doesn't exist. Probably a lot of you already know about this. And of course, it is even less the case for channels, because as we saw, the controlled version of a channel isn't even well defined in general. I mean, it is an ambiguous notion, and you have to take a cross operator of it to define a controlled version of it. But what's the catch? The catch is that actually there are, and this had been noticed already, there are simple experimental protocols that implement universal coherent controlization. So for two examples coming from a paper by Nikolai Fries, on the left, you have an implementation with optical systems. So here the idea is that the target system is a photon. Depending on its polarization, that will play the role of the control here. Depending on this polarization, the photon will go into either of two paths, and in one of the two paths, it meets a channel U. It meets a gate U, and then, well, U is applied only, of course, if the polarization was in the right state. So you have a coherent controlization of U. In the case with ions, to put it very quickly, the idea is that you have a qubit that consists in electronic levels, and then you can implement a first pulse to possibly store this system into different energy levels, and then you apply your pulse given by U. And if your states have been stored in the other energy levels, then U is out of resonance, so essentially it does nothing to them. Whereas if you have, if you didn't do anything to them, U will then be in resonance and implement a transition between two energy levels. So in this way, same thing, you can implement a universal controlization of U. So now, how does this work? How is it possible when we said that when we saw this no-go theorem? Well, and once again, what I'm going to say here is not particularly new. This is something that had been noted already. The resources that are used here are not exactly channels on the target system. For example, in the optical system, this gate hue that you see here, so for example, it could be an optical element, a phase shift, for example. Well, of course, it is possible that the photon goes through this optical element, but if the photon goes the other way, then nothing goes through this optical element, and you have to say something about this nothing, and you define it through vacuum states and so on. Therefore, this optical element cannot be only defined to act on the photon. It has to be defined as acting on either the photon or the vacuum. With the ion implementation, it's essentially the same thing, because now your pulse is not only acting on the two levels with which it is resonant, it is also acting on the other levels, even though it is out of resonance on these other levels. So you still have to define it mathematically as acting on a bigger systems than just the two levels. So now our point will be to describe these implementations, because these are the ones who work, and to study them theoretically. So to study them, we will use sector preserving channels, which weren't called this, but which are essentially in the spirit of the reference that you can see at the bottom. So the point is to take a Hilbert space that has a partition into sectors, for example, into two sectors. So by a sector, we mean an orthogonal subspace. So it's just split into a direct sum of two orthogonal subspaces. And then saying that the channel is sector preserving means that if an input state is in one of the sectors, then under the action of the channel, it is mapped to an output state that is also in the same sector. So you can define it like this. And in particular here, we will be interested in the case of a partition into two sectors, and one of these sectors, the sector not, having dimension 1. So it would be interesting to look at how you characterize such channels. Now, the naive way to go about it would be to say, okay, the sector 0 is of dimension 1 anyway. So you know, your channel is just acting trivially in it. So talking about such a channel is the same thing as talking about a channel on the D-dimensional system. Now, of course, probably all of you have guessed already that this is not the case, because there could be coherence between the two sectors. So a one-to-one characterization, and this is probably going to remind you of something, is given by choosing a channel on the D-dimensional system and then picking a pinned Krauss operator of it. And the way you do it then is that you take the pinned Krauss operator to be C1, and you say that C1 is the one that is going to have full coherence with the 0 sector, and the others will have no coherence with the 0 sector. Such a channel we will therefore represent as C tilde C1, and we will use the graphical notations of rooted quantum circuits and just say that it goes from Sk to Sk, and the repetition of the superscript k here is here to denote that it respects so-called sectorial constraints. So here it is sector preserving. So now, of course, you see that this is fully analogous to the characterization of a controlled channel. So what we have is that on the one hand, sector preserving channels have a fully analogous one-to-one characterization with respect to controlled channels on the D-dimensional sector. So you have this mathematical equivalence. Now we are going to show that this is not only a mathematical equivalence, this is a physical equivalence, because our resources, you can trade them freely. And the way we will do it is using the control supermap. So that leads us to the yes, please do go theorem, that should be put in contrast to the no-go theorem, that will tell you that there exists a slightly different supermap, a supermap that acts on sector preserving channels. And that this supermap is now such that any sector preserving channel is mapped to the associated controlled channel. So here, changing slightly the definition of universal coherent controlization and saying that now it corresponds to a task that is accomplished on sector preserving channels with a one-dimensional sector. Doing that, then we can say that we have a universal a universal implementation of coherent control. That in particular encompasses all the experimental implementations. Now, what is this controlled supermap? Here you have a formulation of it. It is written in terms of fluid quantum circuits to avoid having to write down annoying some annoying stuff. I mean, it is nicer to write it in terms of fluid quantum circuits. It could also be written as acting on general channels, even though its action on channels that are not sector preserving is not of interest to us, but it could be. This is something we do too, but essentially it's less nice. So that's the controlled supermap. Now, we also have an inverse controlled supermap that takes controlled channels and maps them to sector preserving ones. And essentially you can see that it is an inverse of the controlled supermap. So, if you compose one with the other, you get an identity supermap. So that means that these two resources, controlled channels and sector preserving channels of type 1D, so with one sector dimension 1 and the other sector multidimensional, you can convert between these two resources fully, so they are fully equivalent as resources. Now, let me turn to the case of two control, that is the control between the application of more than one channel. And more generally, I mean, everything I'm going to describe here could be readily generalized to the control between n channels with a control system of dimension n. So we can define a two control supermap that is fully analogous to the other control supermap. And notice here once again that now the input and output systems of the operation to be controlled could be of different dimensions in general. And so now this two control supermap takes two sector preserving channels and outputs the control between those two. Now there's a catch though. In fact, if we use this control supermap, we can only have coherence between one pair of cross operators. That is, the output, the controlled channels that we get from here will be of this form. I mean, you could always find a cross representation of them in this form, in which there is only coherence between one cross operator of the input channel A and one cross operator of the input channel B. So we don't have all the possible versions. There are versions that cannot be put in this way. So we don't have all the possible versions of a control between two general channels. So we have a way of going around this. I'm going to go quickly about this, but the idea is that now you have to use as resources not just channels that restrict your original channel on a sector, but channels that restrict to the purification, or at least a partial purification of your channel on one of the sectors. So then we can define this supermap that has also environments in outputs, sorry, that you can define in terms of the true control. And then, so essentially you need to have an environment, and then the number of cross pairs that feature coherence between them, between the two channels in the controlled channel, this number of cross pairs is capped by the dimension of your environment. So essentially, if you take an environment that is big enough, you will be able to get all the possibilities. Finally, let me go very quickly about another notion of control that we define here and for which we find the resources, which we call composite control. So the idea is that your control system is multidimensional and the target channel is applied only if this control is in 0, but if it is in one of the 1 to m states of a given computational basis, then the identity channel is applied. So we find a general characterization of these channels that I won't describe here. And we find that there is an associated resource that are sector preserving channels with now essentially more than one-dimensional sector. So everything will generalize nicely to the case of composite control. All right, that's it for me. For the outlook, so as you I hope we're convinced in this talk, we saw that the universal coherent control can be implemented if you define it as using sector preserving channels as resources. An interesting experimental outlook would be to focus more on other possible implementation of coherent control, because so far the focus has been mostly on quantum optics. but this could be done using, for example, ions or also superconducting qubits. There are papers from the Freeze group about this. And finally, we have also, in the meantime, defined rooted supermaps. And rooted supermaps are in themselves an interesting mathematical object. So by rooted supermaps, we mean maps that act only on channels that follow a certain route, so that satisfy sectoral constraints. So these supermaps could also be applied to the description of indefinite causal order, but that's a story for another time. That's it for me. Here's a very short summary, and thank you very much for listening to me.